Okay, hello everyone. In section 1.2, we're going to take a look at some techniques for finding limits. Now, coming to this section, in section 1.1, we essentially found limits using either tables or graphs, correct? We really didn't have a systematic way, or let's say an algebraic way of finding the limits. So in this section, we're actually going to take a look at some of the limit laws which allow us to find these limits a little easier and without having to graph or create tables. So there's going to be quite a few of these. I think there's about like maybe 8 of them. So please bear with me as we go through these. So these are again the limit laws that we're going to take a look at. So the first one, first of our limit laws is this one. The limit as x approaches a of a constant is constant. Okay, so for example, the limit of 5 as x approaches 1,000, that's going to be 5. The next limit law is the limit of x. The limit of x as x approaches a number is just you plug in for x the a, and it's going to be a. So it's direct substitution into that one. Okay. Now for the next few limits, well, actually, let me see. Let's take a look at this next limit law. This one, the limit of, let's go a constant multiple this time. C is a constant here. C times f of x is going to equal to a constant times the limit of f of x. I'm assuming limit of f of x is L, so let's write that. So we want to make the assumption that you're going to say let the limit of f of x be L as x approaches a, and let's also say that we're going to let the limit of g of x be m, a second function, as x approaches a. Okay, and of course we don't need g yet. We haven't introduced g yet, but so this one, the one that we just did, this one is now okay. Alright, this one. Okay, now let's take a look at our next limit law. This next one is the addition and subtraction law of limits. So it goes something like this. The limit as x approaches a of f of x plus or minus g of x is going to be equal to L plus m. So in other words, the limit of sum or difference of function is going to be sum or difference of the limits of the functions. Okay, this is the addition and subtraction law combined. Next, we're going to take a look at the multiplication law of limits, the limit of f of x times g of x. This one, we can actually write it as limit of f of x times the limit of g of x. Now, both of these approach a, and I know as much pain as it is to write x approaches a every time, but please make sure you write it, otherwise the statement is not correct statement. Okay, so this is going to be L times m. So limit of a product will be product of limits. Next, we're going to take a look at the quotient rule of limits. The limit as x approaches a of this time, I'm going to have f of x divided by g of x. I'm not sure what happened there. Let me rewrite this one. G of x, and that's going to be equal to L over m, provided of course g of x doesn't equal to, or not g of x here because we're looking at the limit. So let me just put the limit here. The limit of the denominator cannot be 0. And that's obvious, right? Because division by 0 is undefined, and that is the reason. The next limit law, the limit as x approaches a of, we did the constant multiple, right? So let's do the root, the nth root of f of x. We can write this actually the nth root of the limit of f of x. as x approaches a. And remember, the limit of f of x was L, so that's going to be the nth root of L. Now for this to work, of course, the index of the radical has to be what? Positive, 2, 3, and so on. Correct? And L must be positive in this case. Limit has to be positive if the index is even. And the reason for that is because if L is negative, for example, I get in a situation like this if I have a square root of -5, if the limit is -5, and this is not real. And remember, in this course, we're working with functions of real variables. Okay? So, and in fact, through Calc 2 and Calc 3, that will be the assumption that all the functions are real valued functions we're working with. The next limit law is this one. The limit as x approaches a of f of x to a power of n, and that's just going to be the limit of f of x to the power of n as x approaches a. And this one is going to be what? It's going to be L to the n power. Okay, and for this one, n must be a positive integer again. N is positive integer. Okay, and the next limit law, let's take a look at this next one. The next one says as x approaches a of x to the n is equal to a to the n. So for this also, you just plug in directly a in for x and you get a to the n. Okay, and this also, n must be a positive integer in this one. N is a positive integer. Okay, now let's take a look at the limit of polynomials next. So for this next limit law, we're going to say if p of x is a x to the n, let's say a n x to the n plus a n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0, then if that is a polynomial function, let me write that is the form that I have implies it, but let's say this is a polynomial function. So being a polynomial function, that means all of the exponents must be positive integers, right? So that's given by the fact that that's the very definition of polynomials. So if that is the case, comma, then we can say that the limit as x approaches a of p of x is simply p at a. So all this means is that in order to evaluate the limit of polynomial functions, you simply plug in for x. Okay, so that's what that is. Now we're going to see a whole bunch of exercises later on, so much so that you're just going to get sick of it. Okay, so for now I'm just going to cram all of these laws for you, and then we'll see at least 20 exercises. So be prepared for a lot of exercises. You might want to grab a cup of coffee or a pot of coffee or get your latte ready here. Okay, so we're going to be together for a while. Alrighty, now our next limit laws involve rational functions. So in this next one, if f of x is, let's say, p of x over q of x, the general form of a rational function. Now remember, by definition of rational function here, p and q are themselves polynomials, right? That's the very definition of a rational function. A rational function is an expression where the numerator and denominator are polynomial functions. Okay, so if that is the case, then the limit of f of x as x approaches a is going to be equal to f at a again. Remember, these are special kinds of functions. So what does f at a means you plug in a into p and you plug in a into q. So each of those polynomials, you evaluate them individually. Now again, anytime we have a division or a quotient here, we need to safeguard again division by 0. So we're going to assume q of a is not 0. Okay. And also, if q of a or q at a is 0 and p at a are different from 0, in other words, the denominator is 0 but the numerator is not, in that case the limit is the good old d n e, does not exist. Okay. So a quick example of this one, let's say I want to find the limit as x approaches 2 of, let me go x minus 2, so I want to make sure I get 0 in the denominator. The numerator doesn't matter, x plus 7. So in that case, the limit is going to be denominator approaches 0, the numerator, because it's polynomial, you just plug in a 2 for x, right? So 2 and 7 makes 9, and division by 0 is undefined, and hence d and e does not exist. Okay. Now again, it could be that it doesn't exist. In fact, let me give you some examples now. Remember, for us, the limits of infinity or negative infinity, those also do not exist. It's just those two, infinity or negative infinity, give us just a little more information about the behavior of the function, whether it approaches infinity or negative infinity. So let me just write what I just said here kind of in more details. So let's say for rational functions now, so rational function where q of x is equal to 0, we have two cases. In this case we have two cases. Okay, so what are the two cases? Now we have p over q, right? In this case p does not approach 0 but q approaches 0. Okay, so that's one, the first case, right, which is the one I just mentioned. In fact, you're looking at the example directly above it. If the numerator doesn't go to 0, the denominator goes 0, then the limit does not exist. Okay, so if that's the case, then we just said that the limit does not exist. Now, to delineate or to differentiate between does not exist in the form of whether does it not exist because the left right hand limits are different, or is it because the function goes to infinity or negative infinity, let's take a look at three examples of this. So in all three examples here, we're going to have a numerator that's not going to approach 0 in the limit sense, but the denominator will. So the first example, f of x is 1 over x minus 3. Then let's say my other function is f of x equals 1 over x squared. And last one, f of x is equal to negative 1 over x squared. Okay, so I just made up some simple basic functions here. All right, now if I take a look at the graph of the first one, okay, so let's say this is a vertical asymptote at x equals 3 because division by 0 undefined at when x is 3, you get the 0. Okay, now this function, if you look at the graph of it, this is how the graph of this function looks. Okay, you can graph it on a graphing calculator and see it. So here's the case where, and in this case, let's say I want to know if I want to find the limit as x approaches 3 of f of x. Now, because the right limit approaches infinity, the left hand limit approaches infinity at 3. So for this one, the limit truly does not exist, means it's not getting very large and it's not getting very small. So it's behaving differently from the right and from the left side. Now for the one that's in the middle, this one, if you graph this function's graph actually looks like this kind of. Okay, and here is 0, division by 0 undefined, and we want to find the limit as x approaches 0 of f of x being what it is right now. Now again, as you go to 0 from the right, it's shooting up to infinity. You go to 0 from the left, it's shooting up the infinity, right? So in both cases, the function is getting very large. So this limit we actually say is infinity. You see that? Again, that limit doesn't exist. It's just telling us a little bit more. Okay, this function gets very large near 0. That's what this says. And let's take a look at the negative of what we just did. Would actually reflects therefore, right? Because negative in front of a function reflects the original function. And there you have it. Here's x, and there's my 0. So for this one, if I look at the limit as x approaches 0 of this now being the new f of x, this one coming from the right, the function is going to go to negative infinity. Approaching from the left, again, it's going to go to negative infinity. And there you have it. Okay, so with rational functions, if the numerator, again, this is when the numerator is not 0, please keep that in mind. That's important. See right up here. The numerator cannot be 0. If the numerator is 0, we get into what we call an indeterminate form of 0 over 0. And those must be handled appropriately. Okay, and we will see example of that later on. So hopefully so far you're good. Nothing earth-shattering, but again, interesting, better than last time, right? First section. Now let's take a look at, we're gonna get into some theorems now. There are, I believe, more specifically, let me see how many theorems I counted, including this one and this one. Okay, so I'm looking at 5 theorems. So let's take a look at these theorems now. So first I'm going to look at Theorem 1 in your book. Theorem 1 is actually pretty simple. It's more of those kind of limit laws. So it's going to look at limits of trig functions. Can't leave those behind, right? Mathematics wouldn't be the same without trig functions. They really spice up everything. If a is in the domain of the trig function, if a is a number in domain of the trig function. Now remember, we have 6 trig functions, right? Basic trig circular functions, sine, cosine, tan, cotan, secant, and cosecant, right? So we're going to look at those. So first, let's begin with the limit of sine x is going to be sine a as x approaches a. The limit of tangent of x is equal to tan a as x approaches a, and the limit of secant of x is equal to secant of a as x approaches a. Now the other 3 are the cofunctions of these functions. So for example, the cofunction of sine is cosine, right? And that in fact what that co in cosine stands for. Cosine x means cofunction of sine x. Okay, so cos x as x approaches a is equal to cos a, and cofunction of tangent, that's going to be cotangent as we approach a of cotan x, that's going to be cotan a. Again, each of these must be defined in their respective domain, and they have some of them have a different domain than others, right? So for cosecant x is going to be cosecant a. And there you have it. Okay, it's a pretty basic, simple, easy to follow. Then let's take a look at Theorem 2. In Theorem 2, this is a very interesting theorem, the one that is used throughout this course and also in your second and in third semester calculus. Okay, so this one is what your book calls it, the Squeeze Theorem. Now, some other textbooks call this the Sandwich Theorem. Just like a sandwich, you go to Subway sandwiches, that's exactly what that is. It is a sandwich. So, squeeze or sandwich theorem. Now, for this one, in order to actually use squeeze theorem, we need to have three functions. So, suppose, let's say we have f of x, and we're going to make him like this. Let me make it f of x to be less than or equal g of x less than or equal to h of x. Okay, and this is true for all x. So, sidebar, the symbol here, this is a universal modifier. Okay, this means it means for all, for every. Okay, so that would be the universal modifier. I will be using some of these throughout, so you just kind of begin to work with these modifiers to get you ready for your higher courses in mathematics. So f of x is less than or equal to g of x less than h of x for all x in an open interval containing a except possibly at a. Just like we did before. Remember, in order to have a limit, we have x must be in an open interval. So, except possibly at a. Now, the reason we have except possibly at a again, remember, because the limit, the function at a need not be defined in order for the limit to be defined. Okay. And so what's going to happen as a result? As a result, we're going to say that the limit of f of x is equal to L. Suppose the limit of the first function is L, and that's the same limit as the upper function h of x. Okay, as x approaches a. So, because the lower function is L, the limit of the lower function is L, the limit of the upper function is L. Therefore, the middle function, which is bounded by the two or sandwiched between the two, or it's being squeezed by the two function, has no choice. And then in this case, we say that the limit of g of x is equal to L. So g of x is the middle function. Okay. Now, as far as like the a schematic of this one, so let me see if I can draw this. Let's say I'm going to make up a function. So here's the higher function. This is going to be h. And the lower function, I'm going to go, these are actually touching here. Okay. This is the lower function. That's going to be f. Now we're going to make g to be some function like this. Okay. Could do something like that. Some weird function. So the point being that g could behave however it wants to. What's important is what's happening at a. So at a, actually, g is being squeezed by the other two functions. Only right in here, okay, at a in the neighborhood of a. So that's what the sandwich theorem says. Because g is sandwiched between the other two functions, therefore its limit has to be exactly the same as the other two functions' limit. This case, L is the limit. Okay. And there we have this one. Now we will be doing an example of these again in a few minutes. I just want to make sure we get through these, and then we'll look at a whole bunch of exercises. Let's take a look at Theorem 3. Okay, Theorem 3 goes like this. This is pretty light-hearted theorem. Let function f of x be less than g of x. Now in terms of like the graph of the function, when we say f of x is less than g of x, means we have something like this. There you go. The higher function is f, the lower function is g. That's what that means. Okay, so, oh actually I got it backwards. I know most of you caught that, right? F is the lower function, g is the higher function, the upper function. Remember, this is larger, right? So we have f of x less than g of x, and that's true for all x. And just like before, in open interval containing a, point A that is, except possibly at A. Except possibly at A, and so further, suppose that the limit of f of x is L as x approaches A, and that the limit of g of x as x approaches the same value is m. Therefore, L must be less than or equal to m. There you have it. So for the higher function, at that same point, and I can actually show you on this one, there you go. Let's say this is point A. And at the limit, this would be, for the lower one, it's going to be L, and this is the limit for the higher function, m. You see that m sits above L. So that's what this theorem says. Okay. Now let's take a look at our next two theorems. Are very interesting indeed, folks. Okay. And then I'll try some examples for you. So this next theorem, Theorem 4. Okay, let's take a look at this theorem. Let me scoot this thing up. Okay, Theorem 4. Theorem 4 is the first of the two limits involving trig functions and transcendental, trig function and algebraic function. And that's what this one is. It goes, the limit of sine theta over theta is equal to 1. Okay, and that's what that theorem says. And we're going to actually prove this theorem. Okay, so in order to prove this theorem, I actually need to begin by making a drawing here. So in the interest of time, I'm just going to pause the video, and then I'm going to draw something real quick, and then we'll prove this theorem. Okay, so there I have it. So I have a unit circle drawn here for you. So this is a unit circle, meaning it's a circle of radius 1, right? So here I'm going to put one here, one here, one here, and let's say one here. So keep that in mind, please. This is a unit circle, a circle of radius 1. Now I'm just going to draw a random line, okay, line L that runs through the origin. Okay, so, and I did. So here is the line that I just drew. Okay, so I have the unit circle, and this is just some random line that runs through the origin. And I went ahead and labeled these points O, P, and Q. Okay, now I'm going to go ahead and construct a triangle here. Okay, and the way we construct a triangle, let's see if I can do this. If it doesn't work, then I have to pause the video and do it in another way, but I think this should be okay. So here's, I'm going to draw the first triangle. Connect from P to Q. Okay, so there's one side of that triangle would be OPQ. Okay, and maybe make it a little darker. Okay, so there's my triangle that's constructed. Now the coordinates of the points, let's actually write these coordinates as well. Okay, oops, sorry. So I'm gonna actually write these coordinates as coordinates P is x comma y. Okay, and let's see, that's this point. If I drop a perpendicular here, then this height is going to be y, and the width of this triangle is going to be x, right? Because the coordinates of the point are x, y, so distance from the origin to here, this is x, and y would be the vertical distance from P down to the x-axis, right? So there you go, that's what y is going to be. Okay, now the angle, this would be angle, call that angle theta. So far so good. And then I'm going to draw a line that is tangent to Q. Okay, so it's tangent to the circle at point Q. So let me draw that tangent line now. Okay, so I drew the tangent line, and that would be this line. This is the one that I just drew. Okay, that would be the tangent line. Now I'm going to label this point, this would be point R. Okay, now point R, we are interested in the coordinates of that point. Okay, well, we know the x component of that point, right? Okay, so the x component of the point, right, because it's tangent to the circle at point Q, so the x component of it is going to be 1, right, because this is a unit circle, right? There's your 1 right in here. Distance from O to Q, which is directly above or below point R, is that. So the question is, what is the y component, right? So let's try to figure this out. Now, this line has a slope, right? So we can actually find the slope of this line. Okay, so the slope of a line, well, before I do a slope of a line, let me show you another thing here that's going to come handy. If I look at cosine theta, remember cosine is the ratio of adjacent to hypotenuse, right? So I'm looking at cosine of theta right in here in this triangle. You see the y here? I'm looking at OP and this right triangle. So in this right triangle, cosine of theta is adjacent 1 to, the adjacent is x. Let me now remove this so it doesn't confuse you. There you go, the adjacent is x now. And the hypotenuse is 1 because that's the radius of the unit circle. So the cosine of theta is going to be adjacent over 1 or just x. Sine of theta is going to be opposite, which is y over hypotenuse, or y. So in other words, the coordinates of this point pxy are cosine theta comma sine theta. And you probably remember that from your trig classes, right? For a unit circle, x equals cosine theta, y equals sine theta. So the slope of the line, m of L, right, is going to be the ratio of y to x, true? And y is sine theta divided by cosine theta. So that ratio is tangent of theta. So now we have the slope of that line, okay, what we call the secant line. So the slope of a line is tangent of theta. Now from that we can actually find this unknown component now, right? And here's how. We can write tan theta as tangent theta over 1, right? So that would be, now I'm looking at this triangle. I'm looking at the triangle, it would be ORQ. Okay, so I'm looking at triangle ORQ. Okay, in ORQ now, if you look at the slope of the line from ORQ is going to be the rise, which is, let's say, slope is the question mark, right? Over the run is 1. And the reason is because the distance again from O to Q is 1, right? Again, I'm looking at this triangle, folks. ORQ. The horizontal distance is OQ. The vertical distance, this side is, call it question mark or Y. Okay. And let me in fact put Y here. The reason I didn't put Y because I don't want to confuse it with the Y that's for point PXY. So there you go, call that Y. So the slope is Y over 1, isn't it? That would be rise over run. Now, but we just found the slope of the line here, right? To be tangent is the same as the one before. Therefore, tan theta over 1 is equal to Y over 1. So from this, we get Y is equal to tan theta. In other words, we found the coordinates in the Y component of point R. Okay, that's tan theta. Now that we have this, let's actually try proving this using the Sandwich Theorem. So we're going to take a look at 3 regions here and see if you agree with this statement or not. If I look at the area of the triangle OPQ, that's going to be less than or equal to the area of the sector OPQ, and less than or equal to the area of triangle ORQ. Now, what is the sector? I think the other 2 triangles you can see. The OPQ, here's OPQ. In other words, what we're doing is we're looking at this portion of the circle. Let me do a rough sketch and a blow up of that piece, what's going on there. Okay, so this is what we're looking at, folks. This is the part of the circle that forms an arc, right? Okay, an arc of a circle. That's the arc of the circle. And this is where Q is. This is the part that we made a perpendicular distance from P down the x-axis. This is point P. Okay. And the other one was when we drew a tangent line, and there's extension of that line, and this is R. So this is exactly what's going on. The area of OPQ, that would be this triangle, okay, is going to be less than the area of the sector. The sector is the part that actually curves. There you go. This is the sector OPQ. See that area? It's bigger than the area of OPQ. Okay. Hold on. Something is not quite right here. This is the triangle OPQ. Okay. Now that's better. So let me for now remove the Y and this one. Sorry about that. Okay, there you go. That's OPQ. So up here, actually, I'm looking at, there you go. That's the triangle. The sector, again, is the part that bends, the one that curves, and the bigger triangle is ORQ. All right, now we have those triangles all figured out. Now the area of OPQ, this triangle OPQ, is going to be 1/2 base times height, right? The height was Y, remember, and the base is 1. The distance from O to Q is 1. So it's going to be 1/2 base times height is Y, but then Y is sine theta. Now the area of a sector, let me put that here. The area of a sector is 1/2 R squared theta. That's from your trigonometry. I know you probably don't remember that, but that's what that is. So it's going to be 1/2 times R is the radius again. R is 1 squared times theta in radians. And the area of triangle ORQ, the larger triangle, is 1/2 base. Base is OQ1, and times height. Remember the height? We found it to be tangent theta. And there, we were able to create an inequality. Now let me tidy up this inequality for you here. So this is, if you multiply all three parts of inequality by 2, the 1/2s drop. So I'm just going to cancel the 1/2s. First part is just sine theta, second part is just theta, and the last part is tan theta. Okay, now next step, we're going to divide everything by sine theta. Okay, so I'm going to divide by sine theta, and by sine theta here. Now sine theta over sine theta on the left side, that's 1. In the middle we have theta over sine theta, and tangent over sine, well, tangent is sine over cosine, true, divided by sine theta, give it the denominator of 1, invert and multiply, 1 over sine theta. You can cross out sine theta and you get 1 over cosine theta, which is of course secant, right? But we don't want to write it as secant. Let's just keep it as 1 over cosine theta. And the reason is this, because we want to prove that the limit of sine theta over theta is 1. Now if you note in here, we have actually built to almost what we want to show the limit for. So at this point, to get exactly the function that we're looking for, let's flip the fractions. Now when we flip the fraction, you flip a 1. In other words, you take the reciprocal of those. The reciprocal of 1 is 1. When you flip the middle fraction, you get sine theta over theta, which is the form of what we want. 1 over cosine theta, you flip it, you get cosine theta. Now once we flip, actually the inequalities will change direction, right? And here's why. Let's say I have 1/4 is less than 1/2. Agree? If I flip the fraction, this becomes 4, that becomes 2. I need to change the direction. So when I change the direction, now it reads correctly. So we did exactly just that. Okay, it's for that reason. So we were able to bound this sine theta over theta. Now let's actually write it in the form where we usually like to see our inequalities going right in this direction. So I'm going to flip everything. I mean, not flip it as in, I'm just going to notice the way this thing reads is that 1 is bigger than sine theta over theta, and sine theta over theta is bigger than cosine. Well, that means cosine is the smallest thing. So I'm going to write cosine theta is less than or equal to sine theta over theta, and that's less than or equal to 1. Okay, now that's exactly what we have, right? Let's actually take the limits now. The limit of cosine theta as theta approaches 0. Remember the theorem for limit of trig functions. You plug in 0 for theta, and cosine of 0 is 1. Let's do the limit. So this is would be f, this is g, and this is h in our theorem for Squeeze Theorem. And here we have the limit of 1, that's our function h. The limit of constant 1 as theta approaches 0 is also 1, right? The limit of a constant is constant regardless of what theta approaches to. So the limit of f, the limit of this function is 1, the limit of this function is 1. G is sandwiched between them, or being squeezed or trapped. It's being trapped by the two functions, therefore that limit has to be 1. So from this we can actually imply that the limit of sine theta over theta is 1 as theta goes to 0. And there you have it. Now here, by the way, so hopefully you got this part right. And before I actually move on, let's do this. Our assumption here was that theta is between 0 and, let me write that. We are assuming that theta is in the first quadrant, right? But since we're saying we're approaching 0, that means we should approach 0 from the left and from the right. So in other words, I'm approaching, theta becomes 0, it's going in this direction, right? I'm up here. It's going in this direction, approaching 0. Now we gotta look at it approaching 0 from below, right? In this direction. Theta approaches 0 from below. Theta approaches 0 from above. Okay, so we just did it from above. Let's do it from below. When theta is actually a negative angle. So for this part, it won't take long. If theta is actually less than 0 now. Okay, so that means we're going to take now theta to belong to negative pi over 2 and 0. Okay, so in other words, again, negative pi over 2 and 0 means we're going in this direction. This is negative pi over 2, that's 0. Okay, we're going in a clockwise direction, so the angle is negative. Now for negative pi over 2 to 0, our expression becomes, remember, cosine theta is not cosine negative theta, is less than or equal to, instead of sine theta over theta, we have sine negative theta over negative theta, and less than or equal to 1. I'm looking at this inequality, making it work with negative theta there. Okay. Now, let's do this. Let's rewrite the expression. Now remember, the negative angle identities, the cosine of negative theta is the same as cosine theta. That's because of negative angle identities. Some say that's because cosine is an even function. But however you say it, either from identity or being even function. Sine of negative theta, sine is an odd function, so sine of the negative angle is negative sine of the positive angle. And of course 1 is unaffected. Now if you work this one, in the middle, negative by negative is positive, and look what we get. We get exactly the same expression that was above, that we just found a limit for. So this is exactly the same as this one, right? And we showed the steps thereafter, how that was done. Okay, now let's actually see. So that proves the theorem. Again, that's why I don't go through a lot of theorems in this course, because they just take up too much time. I rather actually do more example and exercises, and I'll do that in the future. It's just this one is a classical one. It's interesting to see how Theorem 4 worked. And there you go. Now, you want to remember this theorem, okay? So limit of sine theta over theta is 1. Now, one thing, let me make something quick here. When we say theta is a measure of an angle, right? So if I want to find the limit of theta going to 0 of sine 700 theta over 700 theta, you see that? That's the measure of the angle. As long as the argument of sine and the denominator are the same, this is going to be 1. Why? Because it's in the form sine theta over theta. These two must be the same. Okay? And there we have it. Let's take a look at another example. Let's say I want to find limit of theta going to 0 of sine 5 theta over 2 theta. Okay, now this is interesting. Notice the argument of sine and the denominator are not the same, right? So that limit is not 1, right? It's not 1 because I don't have 5 theta in the bottom. But whatever the argument of the sine is, which is 5 theta, you want to create that in the bottom. So how am I going to create it? Well, 2 theta isn't going to help me. What 5 theta would, wouldn't it? So let's multiply the bottom by 5, top by 5. And I'm just going to rewrite this as 5 sine 5 theta divided by the 2 I don't need, and then multiply 5 times theta, I get 5 theta. See how that worked out? I built to the argument of sine. This is what we want. You see that? Now, limit of a product of limits, so I can think of this as limit of 5 halves, right? Times limit of sine 5 theta over 5 theta as theta approaches 0. Now this limit is 1. We know that. And limit of a constant is a constant, so the limit is 5 halves. You see how that worked? And there we just did a couple of examples. Okay. Now let's take a look at another theorem, and then we're gonna look at, I promise you we do 20 problems, right? So I hope that you guys are still awake. I'm sure you are. You're a very dedicated group, I know that. So let's take a look at this. And the other thing, by the way, as I'm writing this, if you get tired of watching these videos, folks, you don't have to do it all in one sitting, right? So it's like, oh, I had enough of this. Just take a break, pause the video, just remember where you left it off. Go out and enjoy some nice heat outside. Temperature near 95 degrees, enjoy the heat, and then come back inside and do some calculus stuff. So here we go. Now we're going to find the limit as theta goes to 0 of cosine theta minus 1 over theta. This limit is 0. Okay, now we're not going to use geometry to prove this. We're going to actually prove this, and the proof won't take long. It does require that we know a little bit about our trig identities. In fact, let me do that on the side here. Remember the double angle identity for cosine, right? Cosine 2x. Well, there's actually 3 forms of that, right? One of them, just so you don't totally forget this, is cosine squared s minus sine squared x, right? That's one of them. If you use Pythagorean identity to rewrite either cosine squared or sine squared, the other version becomes 1 minus 2 sine squared x. And if you rewrite sine squared as 1 minus cosine squared, then you get 2 cosine squared x minus 1. So remember, there are 3 versions of this identity. Okay? All right. Now, the one that actually I'm going to use is this one. Okay? So let's prove this theorem. So to prove it, I'm just going to rewrite the problem, the limit, as theta approaches 0 of cos theta minus 1 over theta. That's going to equal to limit of, now I'm going to use this double angle identity, right? How is this going to work? Oh, let me actually, because, okay, well, I haven't finished it here. Sorry, let me go back. I'm going to let theta equal 2x here. Okay, my double angle, I'm going to call it theta. Well, if that's the case, then divide both sides by 2. Isn't theta halves equal x? I divided both sides by 2, right? By 2, and that's what you get. Now, so instead of cosine 2x, I'm going to write cosine theta. And that means instead of x on the other side, I have to write 2 cosine squared x. Actually, sorry, so sorry. I'm using this version, right? Okay, so I'm going to write cosine of theta is equal to 1 minus 2 sine squared x, which is theta halves. Okay, now subtract 1 from both sides, you get cosine theta minus 1 is negative 2 sine squared theta over 2. Okay, now we're good. look at the numerator in our limit. It's exactly what we just derived, right? So I'm just going to write limit. Instead of cosine theta minus 1, I'm going to write -2. Shucks. What happens is this erase button on my pen is too close to my finger, so just keeps erasing things for me. -2 sine squared theta over 2 divided by, and in the denominator, what do we have? We just have theta, right? Okay. Now, we're going to rewrite this as the limit as theta goes to 0. Now, we're going to work this, actually, let me pull that -2 out, right? This one. We're going to pull that -2. Remember, one of the limit laws was the limit of a constant multiple of a function. It's constant multiple times the limit, so I'm just going to pull the -2 out. You cannot pull the variables out, folks, so I couldn't pull theta in the denominator out, okay? Only constants. Now, sine squared theta over 2, isn't that sine theta over 2 times sine theta over 2, right? I have two factors of it. And the theta, I'm going to put it here, and then just theta times 1 is theta, right? Again, the idea is, this is what I have, right? Now, remember what we did up here? I mentioned as long as the argument of a sign is this, what's in front of the sign in parentheses, okay? As long as the argument of a sign is equal to the denominator that we can use the theorem for the limit of sine theta over theta. Well, look at this one. In bracket, I have sine theta over 2 over theta. I don't quite have theta over 2. So what I'm going to do is I'm going to multiply this times 1/2, right? And multiply the numerator times 1/2. Okay. That times 1/2. The half that's in front of sine theta now multiplies by -2 in front. That makes it -1, right? I'm looking at this product. A half times -2 is going to be -1. And this is going to be...
I can learn.
Sorry about that. We can all learn. Okay, and then this is going to be the limit as theta goes to 0 of sine theta over 2 divided by theta over 2 times sine of theta over 2. And there we have it. Again, using limit laws, limit of a product of the limits. So the first limit, sine theta over 2 divided by theta over 2, this limit is going to be 0. No, I'm sorry, 1. And the limit of sine theta over 2 as theta goes to 0, direct substitution, times, let me write it one more time, sine theta over 2. For this one, you just directly plug in 0 for thetas, which makes it sine 0, which is 0. That's -1 times 1 times 0 equal goose egg. And there you have it. So that proves this theorem. Okay. Now, we do want to remember this theorem. Maybe not the proof of it, but we do want to remember the two theorems, very important theorems. And we're going to use these theorems when we actually talk about differentiation. Okay, when we talk about differential calculus, you're going to see these again. Now, maybe this is a good place for you to take a break and maybe do something constructive, do something productive, and then come back, watch the rest of this video. But I'm going to continue on. You can pause me or stop me. Now, one thing I want to do, what I want to do next, I'm actually going to, okay, let's do this. Let's now begin looking at some examples here. Okay. I want to show you how to find the limit of rational expressions. Okay, so in this one, we want to find limit. Okay, the limit as x approaches 4 from the right of 2 minus x divided by x minus 4 times x plus 2. Now this is nice in factored form. Some of the problems, you get polynomial on top, polynomial on the bottom. Keep in mind, try to factor it. Now one thing in all of our limits, pretty much from now on, by the way, folks, direct substitution is not going to work. And here's what I mean. If I plug in a 4 into this right now, 4 minus 4 is 0. See? 0 times whatever is 0. So I have division by 0. Now, this division by 0, remember the numerator is not going to be 0 in this case. So it's going to be a number divided by 0. Remember, for rational expressions, if the denominator is 0, the numerator is a number, the limit does not exist. However, it could be infinity or negative infinity, right? When the denominator is 0. So let's see, how do I know if this limit is infinity or negative infinity? And we do not want to graph it, folks, right? Because I don't know how to graph this. And I don't want to put the graphing calculator, or let's say use Desmos and say, here's the graph and that's how you do it. So this is what we want to do. We're going to create a sine chart. Okay, actually this is a number line. Here's my reference 0. Now we're going to look at the numbers that make the numerator 0, each factor 0 in fact, in the numerator and in the denominator. So what makes the numerator of this fraction 0? 2 minus what is 0? 2 minus 2, correct? So here's 2. What makes the factor x plus 2 0? This one. A negative 2, correct? So I'm just going to go negative 2 here. And then what makes x minus 4 0? A 4, doesn't it? So I'm just going to type, or on the number line, here's 4. Okay, remember that's our number line. This is my reference 0. So what you need to do, you need to find what makes each factor 0. Okay, that's what I did. Now once we do, there you go, that's 2, negative 2, 2 and 4, right? Now we're going to actually pick a test point. What we're doing has nothing to do with limit right now. Okay, so let's pick up a test point. A test point would be any point between these numbers, the numbers that made each factor 0. So I'm going to pick, I don't know, 5 is a good test point. And then plug it into the expression. We're going to plug it into this. Okay, a 5. So that's going to be 2 minus 5 divided by 5 minus 4. And 5 plus 2. That's going to be 7. So that's negative 3 divided by 1 times 7. Negative 3, 7. Now, the number, we don't care about the number so much as we care about the sign. So that's going to give me a negative. You've done this kind of work, okay? You've done it in pre-calculus where you had to like find the zeros of a function and then graph the function, look at the end behaviors and all of that good stuff, right? Okay, now I'm going to pick a test point between 2 and 4. Let's say I'm going to pick 3. So the numerator is 2 minus 3, right? 2 negative 3. The denominator 4 minus 3, and 4 minus 3 is, oh I'm sorry, 3 minus 4. I better write it. 3 minus 4, and then it's 3 plus 2. Okay. Now 2 minus 3 is negative 1. The denominator is 5 times negative 4 is negative. So 5 times negative 1 is negative 5. So the ratio is positive. And we get positive here. Another good test point is 0 here. Right? So let's try the 0 for our test point. 0. 2 minus 0 is 2. And 0 minus 4 is negative 4 times 0 plus 2 is 2. Negative 8. Positive by negative is negative. So This will be negative, 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 negative. So you can kind of see how this alternate. Typically, if the factors are not repeated, these will alternate. Now, this is going to make our lives so much easier. So I'm going to approach 4 from the right, correct? I'm looking at the limit now here. Okay, we're approaching 4 from the right. As I'm approaching 4 from the right, so I'm coming now in this direction, right? I'm coming, there you go. Here's 4, I'm coming from the right. And the sign is negative, right? So that means it's going to approach negative infinity. The limit is negative infinity. You see that? Because as you come to 4 from the right on the number line, it's negative. What about, how about this one? The limit as it approaches 4 from the left. I'm just going to call that f of x, of f of x. Well, coming to 4 from the left, remember the sign chart? Positive, and we're coming from the left. That's going to go to positive infinity. You see that? Without actually graphing the function. Now, finally, what about the limit of x approaching 4? Let's see, the right-hand limit, that's this one. This is right-hand limit, is negative infinity. This is left-hand limit, positive infinity. Okay, so in other words, the function is doing, this is what the function is doing. It's doing this, and then it's doing this. Right, going to infinity and negative infinity. So at this point, as x approaches 4, the limit does not exist. And there we have it. And all these limit laws, by the way, I forgot to mention, they apply to one-sided limits. All the limit laws we talked about earlier, they apply to one-sided limits. So there you go. Now, let me give you one to do, okay? So I'm just going to say, try this one. See if you can try it. And I'll, I haven't, no, I won't give you the answer. I'll let you work on it. So let's say you want to find the limit. This time, try finding this limit, if you will. The limit as x approaches 5 of x squared negative 3x minus 10 divided by x squared negative 10x plus 25. Now, let me just tell you, you probably naturally what you want to do, you have a polynomial on top, polynomial on the bottom, and we say you just plug in the number into the polynomials. When you do, you're going to get 0 in the numerator, 0 in the denominator. Indeterminate form of the limit. In other words, 0 over 0 is not 1. Keep that in mind. So you need to work this. And let me give you a hint. Try to factor the top, factor the bottom, and then simplify it. Then use the sign chart, just like I did in the problem directly above it. Okay? So let's see how that's going to work out. So now let me, talking about indeterminate forms, let me just give you, there are other indeterminate forms. It's like, how do we know these are indeterminate forms, right? Other indeterminate forms of limits. Remember, indeterminate means just that you cannot determine. And for example, infinity minus infinity. See, my version of infinity, the number I'm thinking of, could be a heck of a lot less than what you're thinking of. So I cannot say that is 0. For example, my infinity is 1,000. Your infinity may be 990. The difference is not 0. And of course, you can make that as large as you want. So it's not 0. That's the indeterminate form, infinity minus infinity. Another one, infinity times 0. That's not 0. Again, remember, we're talking about limits. You may say, well, but they told me 0 times any number, regardless of the number, is 0. You're right, but we're thinking the limits, so it's really not 0, it's approaching 0, and the other function is approaching. It has to do with approach. Okay, so we are approaching 0, we are approaching infinity. So what is the product gonna be? And that's what this is. The other indeterminate form is infinity over infinity. Again, that's not 1, because they're the same. They really aren't the same. Again, here's my infinity. Okay, and here's your infinity. See, that ratio is not 1. Okay, so it's because these are undefined. Now the other form is 0 to 0, infinity to 0, and 1 to infinity. Okay, so that's what these are. And these last three, you actually deal with those in your second semester calculus, and usually what happens is that you end up taking the logarithm of the expression, and then once you take the log of the expression, it turns it into infinity times 0, which makes it in this form, and then you handle it that way. So all of this you do in the second semester calculus. The ones we're doing here are pretty straightforward, if you can call it that. Okay, let's try another example. This one I'm gonna try is by Sandwich Theorem. Okay, so let's try Sandwich Theorem. An example here is the limit as x goes to 0 of absolute value of x over x to the 4th plus 4x squared plus 7. Okay, and this thing is not factorable. Even if it was, it wouldn't do us any good. And call that the limit of g of x. Not f of x, but g of x. When I'm trying to use Sandwich Theorem, the function we want to find the limit of, we call it g of x. Now, using Sandwich Theorem, okay, using Sandwich Theorem, we need to create, remember this is the form of Sandwich Theorem, FGH, right? So we already have g. G is the function we want to find. Question is, well, how am I going to come up with f and h, right? Which is perfectly legitimate question. How do we know what these are? Well, the short answer is the more you do, the more you get used to stuff, and you just get better at it. Okay? But here's how we do this. For now, let's see if this makes sense to you. Remember, we are approaching 0, right? X approaches 0. So, let's see if you agree to this statement that I'm making. Okay. As x approaches 0. Let's take a look at the square root. I'm going to put 0 for x, 0 for x, and I get the square root of 7. True? So the denominator is approaching 7. True? Now, but it's going to be bigger than 7, right? It's going to be 7 and like 7.001. But the key is that it's at least the square root of 7. Now, let's take the reciprocal of that. 1 over square root of 7, therefore, is going to be less than 1, right? Because this is greater than 1. So if you flip the fraction, remember, you flip the fraction and you change the inequality symbol. So, what have we done here? We actually established the upper bound. There is your h. Okay. For now. Now, here's the thing I'm going to write. And also, because we're approaching 0, the denominator square root of 7 is positive, right? This is positive. Well, if a number is positive, means it's greater than 0, true? So I'm going to say that 1 over the square root of x to the 4th plus 4x squared plus 7 is going to be positive. You can try it. Put 0 in there, you get 1 over root 7. That's bigger than 0. And we just show that it's less than 1, right? And notice how we bounded it. But this isn't quite the function, right? If you look at our function, we have absolute value of x. We don't have 1. So we need to build to this function. How am I going to build it? I've got the denominator. I need the numerator, don't I? Look at this. I'm going to multiply all parts by absolute value of x. Now look at the middle function. Isn't that g? So when we try to do sandwich theorem, you start with an inequality. Somehow you need to bound a function that's very similar to the one you're working, and then build it to the actual function that whose limit you're trying to find. Now 0 times absolute value of x, that's 0. 1 times absolute value of x is going to be just absolute value of x, right? So let me just put that x to the 4 plus 4x squared plus 7. And this is less than absolute value of x. And then we're about to finish this. The limit of 0 is 0 as x approaches 0. We just did this one. We're about to do that one. What is the limit of absolute value of x as x goes to 0? Direct substitution makes that 0, doesn't it? That's equal to the limit of the absolute value of x as x goes to 0. So look at it. Your f, and this is your h. The limit of f goes to 0, limit of h goes to 0, and the middle function is trapped between. It's being sandwiched between the two. Therefore, the limit of g of x is going to be 0. Oops, I don't know what happened. Is going to be 0 as x goes to 0. So I know it may not be intuitive, but that is how most of limits of this type work. Now let's actually take a look at something I want to show you. Okay, let me go to Desmos. I want to show you the sine theta over theta thing, because the limit of sine theta over theta is 1. That means the ratio is approaching 1. So we can actually also prove, and we can get from that the limit of theta over sine theta is 0 also. Now let me just put notes, because sometimes we use that in another form. So if limit of sine theta over theta is 0 as theta goes to 0, then let's say limit theta goes to 0 of, let me not say then, but let's say here's what I want to find. What is the limit of theta over sine theta? Actually, sorry, that is a 1. Sorry about that. Okay. So what is this limit going to be? Well, it makes sense. That's going to be 1, 2, right? If the ratio top to the bottom is 1, means they're approaching the same value. Well, you flip the fraction, it's going to stay 1, doesn't it? And in fact, we can prove it this way also. Here's how. We can write limit sine theta over theta. Isn't that as sine theta over theta divided by 1, right? So for this one, let's see, we can actually flip the fraction, or here how I can write it is like this. Let me write it in this form. That's equal to limit as theta goes to 0 of theta over sine theta over 1, right? And let's see, hold on just a moment. Okay, actually I went ahead and erased what I had. Let me do this way. This is much easier. I'm just going to write limit theta goes to 0. Remember, this is what we want to show, right? So I'm going to, in that box, I'm going to divide top and the bottom by theta. Theta over theta. Hold on. So that's going to be theta over theta divided by sine theta over theta, right? Now, that's the limit as theta goes to 0. Theta over theta is 1. And sine theta over theta, right, is that. Now, in the denominator, you're dividing 1 over a fraction. You're going to invert and multiply the fraction. So it's going to be theta over sine theta, right? And that's going to be equal to 1. Okay. So there we have it. And the reason again is for this one, the reason this is right in here because this limit is 1. That's the limit of 1 divided by the limit theta goes to 0 of sine theta over theta. See that the top is 1 and the bottom is 1, and that's why this is true. Okay, so the graph of these, by the way, will be different, right? I'm going to go to Desmos and show you the graph, but just keep that in mind. Sometimes we use limit of sine theta over theta equal 1 or limit of theta over sine theta equal 1. Now keep in mind theta has to approach 0, so if I have, for example, theta approaches pi over 4 of sine theta over theta, that's not 1. Just because it's sine theta over theta doesn't mean the limit is 1. That has to be 0. Okay, so please keep that in mind also. Now let me go to Desmos and I'm going to graph both of these, and you'll see both limits on the graph. That's going to be 1 also. Okay, I'm in Desmos, so let's actually do the first one. Let's do sine x over x. So that's sine x divided by x, and there you have it. That's this one. Okay, so that limit on the graph, again, this is what the graph of the function is, and if you hold the mouse over it and you click, you see at 0 it says undefined when x is 0, but the limit from the right and from the left are approaching 1. Now, to show you the other one, let me do this. Let's actually do now the limit of x over sine x. X divided by sine x. This is going to look interesting. Check this out. And now, look at this function. There you go. This is what the reciprocal function looks like. So they're not the same functions. Sine x over x, x over sine x, they're totally different functions. But in the neighborhood of 0, they are behaving the same, right? Very interesting looking graph. Now, let's actually enlarge in the neighborhood of 0. Gets bigger and bigger, and you will see why the limit is 1. And there you have it. This actually does a pretty good job of it. You see, at 1, so focus on 1 here. You see where the blue and the green curve kind of coincide. That's what we're looking at. Okay, so that's where this is. You see right there, that's where the two kind of meet, right about here. Okay, and anyway, I just want to show you there are two different functions, but their limit happens to be the same. That's the point. Okay, so here are the exercises that you're looking at in your book. Now, I'm looking at the first few problems. These are actually pretty easy, very straightforward, and I can see in all of these, you just plug in the number, folks. You just directly plug into the expression and you get the limits. So for example, let's say, I don't know, problem number 7, x approaches 1. Put 1 on top, 1 on the bottom, and here these should add up to a number in the bottom. You get 3, the top you get -1, -1/3. See that? So all of these you just directly substitute and you get the answer. No problem. Now for something like number 20, secant 2x, well, you plug in 0, you get secant of 0. Now secant of 0 is 1, right? 1 over cosine of 0, which is 1. 1 over 1 is 1. So the numerator in number 20 is 1. The denominator is square root of 4, makes it 2, because 0 plus 4 is 4. So the answer is going to be 1 over 2, 1/2. Same thing with number 22. You plug in pi over 4. You get your tangent of pi over 4 is 1. So the numerator is 1 squared 1. The denominator is 1 plus cosine of 45-degree angle, pi 4. Pi fourth is going to be square root of 2. So that's going to be 1 plus root 2 in the bottom, 1 on top. So you can see these are all direct substitution. Okay. Now, let's take a look at the latter ones, see if there's some of these are pretty easy. Let's see. Go to the next page actually, maybe get more challenging limits. Yeah, there you go, that's what I'm talking about. Okay. These are they got a little more meat, right, on the bone. And there we have it. So let's take a look at maybe some of these. Let's see, probably something where we have to manipulate this. Again, these aren't so bad. These, okay, for all of these folks, try factoring them. Okay, you factor them and then you work them. So let's take a look at, for instance, number 50 together. Okay, so let me pause and then bring number 50 into my notebook, and then we'll work number 50 together. Well, actually, let's not do number 50. The reason in number 50, and I don't know why he has something like this on there. The reason is for number 50, let's see, when you plug in a 1 in the denominator, we're going to get 0, right? T minus 1. You get 0. So we do have division by 0. However, the numerator is going to be 3 plus 4 plus 1. That makes it 8. 8 divided by 0 is undefined, right? So remember, when it's a number division by 0, a number, not 0 over 0, but a number over 0, we need to do a sign chart for this. And in order to do that correctly, I need to know what makes the numerator 0. The numerator is not factorable. And in fact, I just looked at my calculator. The 0 of the numerator is actually in about negative 0.24. So it's kind of messy and it's not factorable. So don't worry about this one, number 50. Let's actually do something like number 52 together. So I'm just going to bring that one, because that is factorable. So we'll do 52, and then we'll do number 56, and then let's see, 58, 60, and then we'll do more of these tricky ones also. So let's begin with number 52. So let's take a look at number 52 here. In number 52, we want to find the limit. So I'm going to write that as limit of. Now we're going to, if you directly substitute in a number 52, if you directly substitute a 2 for v, and in the numerator and denominator, you're going to get 0 in both, right? So we have 0 over 0. Indeterminate form, that means we got to work it through. So that's nu. Actually, it looks like v. The symbol is Greek nu. But we're going to call it a v, so you don't have to worry about that. So we're going to go as v approaches 2. Now in the numerator, I'm going to factor the numerator. Okay, so it's going to be the factored form, difference of two squares, v squared minus 4 and v squared plus 4. And the denominator is going to be v squared minus 4. So we're going to cross out top and the bottom, and then directly substitute. We get 4 plus 4. The answer is 8. And there we have that one. Okay. So there is the answer to number 52. Not bad, huh? Number 54 is kind of the same line, except we got to be a little more creative with that one because it's got radical. Okay, so x minus 4 over root x minus 2. So one thing we could do is we could actually multiply top and the bottom by the conjugate, or we can factor the numerator. Okay, let's do it both ways. So I'm going to multiply by conjugate of the denominator. That is root x plus 2. Again, first, if you directly substitute 4 minus 4 is 0 in the numerator, and square root of 4, 2 minus 2 is 0 also. Now, some multiplying by conjugate of the denominator, root x plus 2, to rationalize the denominator, the limit as x goes to 4. Now, in the denominator, we're multiplying difference of two squares, so that's going to be root x squared minus 4. In the numerator, I have x minus 4 times root x plus 2. So this is going to be the limit as x approaches 4 of, in the denominator, that's x minus 4, numerator x minus 4, and then root x plus 2. Once we get it in that form, we can cross out the top and the bottom. Now directly substitute, we get square root of 4 plus 2. Square root of 4 is 2, and that is a 4. The answer is 4. You see how that works? Let's take a look at another one now. Okay, let's take a look at this one. Again, in this one, as h approaches 0, we have 0 in the denominator. The numerator is going to be square root of a plus 0 minus root a, which is root a minus root a, or 0 also. So this is also in 0 over 0 form. The limit form 0 over 0, which is indeterminate. So that means we need to work it. Okay, the indeterminate form, let me write it here, is 0 over 0. Now, and this is the reason I picked this one, is because we will look at this one actually in chapter 3, I believe. We'll look at this. Maybe in chapter 2. Okay, so again, I'm going to multiply by conjugate. The limit as h approaches 0 of square root of a plus h minus square root of a divided by h. Now the conjugate of the numerator is going to be square root of a plus h plus square root of a, and that's root a plus h plus root a. Okay, now in the numerator we have difference of two squares in factored form. Remember, a minus b, a plus b is in that form, which you get a squared minus b squared. So I'm going to go ahead and write that next. So the limits, call it L, the limit's going to be, that's just square root of a plus h squared. That's the first squared minus the second squared, divided by h times square root of a plus h plus root a. Okay, now in the, what happened? Okay, in the numerator, let's work the numerator out. This is going to be simply, we're going to lose the radicals, right? So this is going to be, and something I did a big boo-boo. I forgot the word limit. You really have to have limit. Without the word limit, these are nonsensical stuff. So that's limit as h goes to 0 of, the numerator is just a plus h minus a over all of the denominator, which is h times root a plus h plus root a. Okay, and now the a and minus a add to 0. And once they do, we can actually cross out the h's now, right? Because this is going to be limit of h divided by h times the square root of a plus h plus root a. as h approaches 0, and this is where, see, the h's cross out, give it a numerator of 1, and this is going to be the limit of 1 over that. And now at this point, because see that h over h, that was the culprit, that was the 0 over 0 part, that's vanished now. Direct substitute 0 for h, this is going to be 1 over root a plus root a, so the answer is going to be 1 over 2 root a. Okay, so there's the limit in number 58. Now, hopefully you follow this. Let's now take a look at some of the trick ones. Okay, so let's take a look at number 68. In number 68, we have tangent of 2x divided by 3x. So now the only thing we had the last two theorems involving sine x over x, and one of them was cosine x minus 1 over x. So everything in terms of trick problems need to somehow be converted into those two. Okay, so let's begin with the tangent. Now we know tangent is ratio of sine to cosine, right? So in number 68, I'm just going to write that as limit x goes to 0 of, instead of tan, I'm going to write it as sine 2x over cosine 2x times 1 over 3x. Okay, that's just the rewrite of tangent. Now I'm gonna remember we need a 2x, right, to go with sine 2x to create a denominator that is 2x. So I'm just gonna actually do that. I'm gonna create a 2x that's in the form sine theta over theta. Okay, now what do I need to do? Well, and then I have 1 over cosine 2x, right? Now, remember, we actually have 3x, not 2x. So I created a 2 and I took the 3 out, didn't I? So why don't I multiply it by 2 and divide it by 3? And there you go. This way I've inserted the 3 back that was there. See, that's 3x. And the 2 that was added as a factor, actually not added as an addition operation, that was inserted as a factor. I'm countering that by multiplying the top by 2. Okay, so I got it in the form sine theta over theta. So the limit is, the first part, this limit is 1. Now directly substitute 0 for x. Cosine of 0 is 1. That's going to be 1 times 2/3. The limit is 2/3. Okay, for number 68. Now let's take a look at number 70. In number 70, one way I can do this one, cosine x minus 1 over sine x. Okay, well, let's multiply by conjugate. Number 70. Okay, so this is the limit as x approaches 0 of cosine x minus 1 divided by sine x. I'm going to multiply by cosine x plus 1 over cosine x plus 1. Okay, so I multiply by conjugate of the numerator. Now in the numerator we have cosine squared x, right? Difference of two squares in factored form. So in the numerator we get cosine squared x minus 1. And in the denominator we have sine x times 1 plus cosine x, right? Or cosine x plus 1, 1 plus cosine x, same thing. Now cosine squared x minus 1, we're using Pythagorean identity, that's going to equal to negative sine squared x divided by sine x, divided by sine x times 1 plus cos x. Okay, as x approaches 0. And then what is the next step? Well, one of the signs cancels, right, from the top and the bottom. And now this is just the limit of negative sine x over 1 plus cos x as x goes to 0, and directly substitute now. Sine of 0 is 0, negative 0 is still 0. The denominator, cosine of 0 is 1. 1 and 1 makes 2. 0 by 2 is 0. It is not undefined. It is not indeterminate. 0 divided by 2 is 0. So that limit is 0 indeed. Okay. And let's take a look at another one. I'd like to actually take a look at something now with maybe Squeeze Theorem, but then there's... Let's take a look at... Let me go back to the exercises. Okay, let's take a look at number 74. This one looks interesting. Now, in exercise number 74, a couple of ways you can do it, the easy way or the hard way. The hard way is to actually use the cosine of the difference between two angles and do that, right? So that would be like cosine plus sine, right? That's one way to do it. And what I mean is that cosine theta minus pi over 2 would be cosine theta cosine pi over 2 plus sine theta sine pi over 2 and go that way. Or the easy way is to recognize cosine theta minus pi over 2 is the same as sine theta. True? And you can see that one easily here. Let me show you this one. Let's say this is theta. Okay, this is a right triangle, right? So that means theta, and call that alpha. Theta and alpha are complementary. They're 90 degrees, right? Now check this out. When we go cosine of theta minus pi over 2, right? That would be the same as sine of theta, right? Cosine theta minus pi over 2 is going to be, because this is shift of sine, so you get cosine theta minus pi over 2 is the same as sine theta. Okay, so let me just call these, let's say here's x, here's y, here's r. So what is sine theta here? Sine theta is opposite over hypotenuse. What is cosine theta minus pi over 2? Well, that's going to be the same thing, right? Or let me actually use this difference one. This is true what I have, but I just want to use the difference formula now. That's cosine plus sine. Okay. And cosine of 90 degrees is 0, right? So that is 0. Sine of 90 degrees is 1, so that's just sine theta, right? Plus 0, which is sine theta. So that's how you can write sine theta. And that's easy now. Remember, we just went through earlier, showed limit of theta over sine theta is 1. And there you go, that's number 74. Now, in number 76, we have tan x minus sine x, right, in this one. So let's work this one this way. We're going to rewrite tangent, right? Let's rewrite tangent as sine over cosine. Okay. So we got some simplifying to do, minus sine x. So that's going to be sine x over cos x, negative sine x, right? Give it an LCD. This is cosine x over cosine x. So I can combine the fractions. Here's the LCD. The numerator is sine x minus sine cosine x, right? Now I can actually factor a sine x in the top. In the numerator, that makes it 1 minus cosine x divided by cosine of x, right? Okay, so let's work with this version rather than that version. So the problem again, number 76, now we can write it as the limit as x goes to 0 from the right of the square root of in the numerator, okay, which is tan x minus sine x. We're going to write that as sine x. Now remember, the denominator is x squared, right? Look at number 76 up here. Denominator is x squared. So I'm going to use one of those x's right now. Write it as sine x over x. And then I have 1 minus cosine x. Use the other x in here. Okay. And of course there's a cosine x which is right in here in the denominator, so I'm going to write that as 1 over cosine x. There. So I spent my x squared wisely in the denominator. And the reason is because the limit of this one is 1. The limit of the middle one is 0, and this limit is 1. So the answer to this is going to be, well, here's my next step. If you want to insert a step, that's going to be limit of a square root is going to be square root of the limit as x goes to 0 from the right of sine x over x times 1 minus cos x over x times 1 over cosine x. And then individually we can use the product rule within the radicand under the radical sign. And you get square root of 1 by 0 by 1, which is 0. Okay? And there you have it. Now, let me actually pick something in the way of Squeeze Theorem. They don't have too many of these, by the way, the Squeeze Theorems. But let's try one. I'm going to go back to the PDF and grab a couple. Okay, so here's exercise number 84. There's actually only 2 of these. I said I'm going to grab a couple, but I'm going to leave one for you. See if you can do number 83. Number 84 is kind of like it. So in number 84, it says use the Squeeze Theorem to find the limit as x goes to 0 of a square root of x cosine 1 over x squared. Now, for all of the functions that either have sine or cosine in them, usually your first step is this one. We're going to bound this function first. So I'm just going to go -1 and less than or equal to cosine of 1 over x squared, less than or equal to 1. Okay. Now, the reason this is true, remember, sine and cosine are range bound between -1 and 1. So this is true for cosine of any angle. So this is like a common knowledge, and hopefully everyone agrees to it. Now, notice we almost have the function. The function we want to find the limit of using Squeeze Theorem. This is your g. We need to find f, g, and h like that, right? So I kind of have f and h, but not quite, because I don't quite have g. So what am I missing to make g what it is, right? Remember, g is this right in here. That's g. I already have cosine 1 over x squared. I only need square root of x, don't I? So let's multiply all 3 parts by square root of x. You see, you try to build to the function that you want to find the limit of. And here's cosine 1 over x squared less than or equal to square root of x. And there you have it. We bounded it. Here is f. This is g, all of it, root x times that, and then this is h. So we need to find now the limit of f. That's the limit of negative root x as x goes to 0, right, from the right. The reason it's 0 from the right is because of the square root. Remember, the domain of a square root has to be 0 or more. So there is no 0 from the left with the square roots. So that's going to be limit of the f, and then limit of g. That's limit of just square root of x as x goes to 0 from the right. Both of those, when you directly substitute 0, you get 0. And by Sandwich Theorem, therefore, the limit x goes to 0 plus, I'm just going to call it g of x, the original problem, as 0. So you can try it. And then it also says that you use a graphing calculator to graph it, which I have in Desmos. Let me copy paste it for you. Okay, there you have it. So this is what the graphing calculator portion is. The problem did ask for this. It mentions verify your result visually. So we found that as x approaches 0 from the right, the limit approaches 0, which is this right here. That's where that is. See that? We're approaching 0. Notice that all in here, the limit is going crazy, right? Bouncing back and forth. But as it approaches 0, then it actually does approach 0. Now, to the right, I have a longer term graph. By that, I mean I extended the x-axis. So you kind of see. So early on, the effect of cosine is very notable and significant on the graph of the function. But as x goes to infinity, the effect of that cosine diminishes, partly because cosine of 1 over x squared as x goes to infinity, well, 1 over very large becomes 0, so that cosine 1 over x squared approaches 1, and the square root of x dominates the behavior of the function, and that's why you see that. This is just like ordinary square root function now, right in here. See, they're the same. It's just in a very small range that effect of cosine is very pronounced on the behavior of the graph. Makes it rather erratic. Okay, and I think we're done, folks, with this section. Sorry, the lecture lasted quite a bit, but I did mention you need to get a pot of coffee or something better. But usually, as we go forward, I'll try to make these lectures complete as possible. And this is just one section. Imagine how long it took. So please don't. I know you get tired listening, watching for 2 hours. So don't do that. Maybe kind of piecemeal that. Watch it for 20 minutes, 15-20 minutes, and then get up, stretch, go do something. Maybe, whatever you want to do. And then come back and watch the video for another 15-20 minutes. So there's kind of a break or a gap between these long videos. But anyhow, we are done. And we did quite a bit, right? Didn't we? I mentioned, something I gotta do. I gotta make sure these are within, they're staying within the boundaries of my, of my recording area. Also, I always make sure that these are neat and that you can actually print these. Remember, I have this available. You can actually print this, and it's going to be like a printed lecture for you, as if you were to take notes. Okay? And anyway, we are done with this, and our next section will be section 1.3. We'll do that in another lecture. Thank you.